Um, okay, so now the next speaker is Nathan Myers. So Nathan, you can start sharing your
All
screen
right.
whenever you're ready.
Okay. Well, first off, I'd like to thank the organizers for giving us the opportunity to get together and discuss some physics in these difficult times. Today, I'm going to be talking also about quantum engines, and in particular, how we can utilize the wave function symmetry, the nature of our particles in the working medium, whether or not they are fermions or bosons, and how that affects the performance of the engine. So the first question we have to ask ourselves is, why are we interested in looking into heat engines at all? Well, the standing goal of quantum thermodynamics is to extend the theory of thermodynamics originally developed for macroscopic equilibrium systems down to the nanoscale systems that are subject to inherent fluctuations arising from quantum effects. And to do this, we need a framework that we're very familiar with, and heat engines provide just such a framework. There's also examples of using heat engines to describe a wide range of natural systems across a whole range of length scales, everything from molecular motors within cells up to planetary scale systems like hurricanes, all the way up to cosmological scale objects like black holes. It's also the practical applications are very straightforward. They're the basis for thermodynamic devices. And ultimately, we're also familiar with the idea of quantum advantage, where quantum systems have potentially additional resources that allow them to outperform their classical counterparts. And we're interested in exploring what sort of quantum advantage may manifest for thermal machines. So a bit of an outline of what I'll be running through. First, I'll talk about the particular heat engine model that we studied here, a quantum auto engine. I'll talk about expanding that framework to a two-particle system, which is the simplest possible model that allows us to explore the effects of wave function symmetry. And I'll talk ultimately about the characterizations of this two-particle engine, its efficiency and power output, the trade-off between efficiency and power, and the parameter regimes where it functions as different types of thermal machines: engine, refrigerator, heater, accelerator. And finally, discuss what the source of the eponymous bosonic advantage is by looking at the instantaneous power. So the particular implementation we looked at is a harmonic quantum auto engine. So the experimental picture to have in mind is two quantum particles within a harmonic trap. In this case, like the classical Otto cycle, it consists of 4 strokes: isentropic compression, isochoric heating, isentropic expansion, and isochoric cooling. Here, the frequency of the trap is or corresponds to the inverse volume in analogy to the classical ideal gas Otto cycle, and the compression stroke then corresponds to increasing the oscillator frequency, and the expansion stroke corresponds with decreasing the oscillator frequency. Something to point out here, Tiago gave us a very nice overview of the difference between quantum and classically adiabatic strokes. So here our isentropic strokes are not necessarily adiabatic. They may be non-equilibrium and have some excitations to higher energy states, some quantum friction involved. And I'll get into that in a little bit. Again, I'm considering a very simple model here, so we're not explicitly modeling the interaction with the heat baths. We assume that the heating and cooling strokes are long enough such that the state of the system can be described at the thermal state after the strokes 2 and 4. So it will be in a thermal state at point A and C in the cycle. So we're all familiar from introductory quantum mechanics that if we have identical particle and identical quantum particles, the overall state of the system must be described as a superposition that is either symmetric for if the particles are bosons or anti-symmetric if they're fermions. This has physical consequences in the form of 2 bosons are more likely to be found at the same location, which is boson bunching. And there's 0 probability to find 2 fermions at the same location, which is a manifestation of the Pauli exclusion principle. Since our engine has compression and expansion strokes, it's very physically intuitive that an effect of attraction or repulsion should play a role in the performance of the engine. Again, we're considering a very simple model, so no explicit interaction between the two particles. In that case, the Hamiltonian just becomes the simple sum of the two single particle harmonic oscillator Hamiltonians. Our first step is to determine the initial thermal state of the two particle system. It actually works out quite nicely to be the symmetric or anti-symmetric combination of the single particle thermal state density matrices with the symmetric combination for bosons and anti-symmetric combination for fermions. If we just plot the position probability distributions from that thermal state, we immediately see the effects of the wave function symmetry. We see for the boson probability distribution that it is stretched along the diagonal, which is representing this effective attraction between the bosons. And we see for the fermion probability distribution, this cut along the diagonal, showing that there's zero probability of finding two fermions at the same location, showing the Pauli exclusion principle in action. Once we have the initial state, our next step is to determine how the state evolves through the unitary strokes of the cycle. To do that, we need the proper evolution operator. And it turns out that the two-particle evolution operator can be constructed from the single-particle evolution operators, which for the parametric harmonic oscillator are studied pretty extensively in the literature. It becomes a symmetric combination or anti-symmetric combination for bosons or fermions, respectively. With the evolution operator in hand, we can then determine the internal energy at each corner of the cycle, from which we can calculate the heat and work, and then the power, efficiency, and all the characterizations that we're interested in. Note in the expectation value terms here, we see a Q star factor showing up for the expectation value of the energy at B and at D. This is a protocol-dependent measure of the adiabaticity of the unitary strokes. So it's 1 for a completely adiabatic stroke, and in general, greater than or equal to 1. So with all the dynamics in hand, we next turn to the characterizations of the engine. We see that the wave function symmetry does in fact play a role in comparison to distinguishable particles. We see for the efficiency that as a function of both the bath temperature ratios and the final and initial frequency ratio, that the bosonic working medium performs better than the distinguishable particles, and the fermionic working medium has reduced efficiency. Note that the particular protocol we're studying here is a sudden switch protocol, which corresponds to an instantaneous frequency quench from the initial to the final frequency. This pattern holds when we move to looking at the power output. In this case, we see again that the bosonic working medium has greater power output than distinguishable particles, and the fermionic medium has significantly more reduced power output. But power and efficiency aren't the only two characterizations we're interested in. If we wanted to just strictly maximize efficiency, we would perform totally quasi-static strokes, completely adiabatic, which would require us to take infinite time, and this would result in identically zero power output. So there's this inherent trade-off between efficiency and power. So a more physically interesting characterization to look at is the efficiency at maximum power, in which we maximize the efficiency, in this case with respect to the frequency, and then determine or maximize the power output, sorry, with respect to the frequency, and then determine the efficiency at that maximum power output. We see again the same pattern holding, that the bosonic working medium displays higher efficiency at maximum power than distinguishable particles, and the fermionic medium reduced efficiency at maximum power. And here we've plotted the efficiency at maximum power with respect to the Kurtz and Alborn efficiency, which is the efficiency at maximum power that the cycle achieves in the high temperature classical limit. We can explicitly quantify this trade-off between efficiency and power in terms of what's known as the efficient power, which is just the simple product of the efficiency and power. Looking at this for the bosonic and fermionic working mediums, we see that the bosonic working medium shows a higher efficient power across the parameter space in comparison to the fermionic medium. So even in the trade-off between efficiency and power, we see that the bosons gain more power per percentage sacrifice in efficiency than the fermions do. the final area that we can look for some sort of or some sort of advantage from the wave function symmetry is in the parameter regimes, where the cycle functions as different types of thermal machines. So we have 4 possible thermal machines. Again, as Thiago alluded to in his presentation, we have the engine, in which we have heat flow from the hot to the cold reservoir, and we extract work from that heat flow. We have the refrigerator, where we put in work to the system to drive heat from the cold to the hot reservoir. We have the heater, where we put in work to drive heat into both reservoirs, and the accelerator, where we put in work to accelerate the flow of heat from the hot to the cold reservoir. From a practical standpoint, the accelerator is our least interesting thermal machine, so to say, because we're just facilitating a process that would already be occurring naturally. If we look at some phase diagrams for the different regimes in which the cycle functions as each type of thermal machine, we see that for the bosonic working medium, we have a larger parameter space where it operates as an engine, as a heater, and as a refrigerator, and a correspondingly smaller space where it operates as an accelerator. And the opposite is true for the fermions. They have reduced refrigerator, engine, and heater regimes, and an enlarged accelerator regime. We can see this explicitly in the third plot here, where we show the region that the bosonic working medium functions as a engine, refrigerator, and heater, where the fermionic working medium does not. So we ultimately want to look at the source of this bosonic advantage. And to do that, we can look at the instantaneous power output during the unitary strokes. For this, we have to move to a slightly different protocol that has an explicit time dependence in it. So we choose a linear protocol in which we simply linearly change the frequency from the initial to the final frequency. Here, I've showed the instantaneous power output for the compression and expansion strokes on the same plot, with the compression stroke on the top and the expansion stroke on the bottom. Here, I'm using the sign convention that work extracted from the engine corresponds to negative power output. We see that the fermionic working medium actually extracts more work on the expansion stroke, but correspondingly, you have to put in more work on the compression stroke. Whereas the opposite is true for the bosons. They extract less work on the expansion stroke, but you have to put in less work on the compression stroke. And this fits very nicely with our physical intuition of this effective attraction between bosons, assisting us on compression and resisting on expansion, and the opposite being true for fermions. So the question becomes, well, why don't these effects simply cancel out? And we see identical performance for both the fermions and the bosons. Well, one thing to note here is that we actually do see that behavior in the limit of quasi-static strokes. So as we move to a completely adiabatic process, the performance of the bosons and the fermions becomes identical. And it makes sense then that the effects of the wave function symmetry should manifest when we're moving outside of the fully adiabatic regime. There, the populations of each energy level are no longer constant. And we have then the Pauli exclusion principle and the boson bunching coming into play in the performance. So to conclude, I've shown we've fully analytically solved the dynamics of a 2-particle harmonic quantum auto engine with a working medium consisting of either bosons or fermions. The 2-particle nature of the working medium opens up a new resource to explore the effects of, namely the wave function symmetry. We've seen that the bosonic symmetry boosts the engine performance, whereas the fermionic symmetry hinders it. And this holds in all of the characterizations we studied, including the efficiency, the power output, the efficiency at maximum power, the trade-off between efficiency and power, as well as the parameter space in which it functions as each type of thermal machine. Since, as I mentioned, we considered the accelerator the least of our physically interesting machines, we consider a smaller accelerator space and larger everything else. We'll chalk that up as another bosonic advantage. It's a little bit of a teaser of the next steps that I've been taking this work, which we should have preprints out on soon. First, looking at explicitly increasing the complexity with an explicit interaction between the particles of the working medium, namely in terms of a contact interaction. And the interesting thing about this is by tuning the strength of this contact interaction, we can change the behavior between bosonic essentially and fermionic. And then also looking at physical systems where we get similar behavior, this tuning between bosonic and fermionic statistics in the form of anyonic statistics, which are quasi-particles that manifest in certain two-dimensional solid-state systems whose statistics interpolate smoothly between bosonic and fermionic. With that, I'd like to thank those that assist me in this work, my group members Priyo and Kram, and my advisor, Dr. Defner. Thank you all for listening.
Okay, thank you very much, Nathan. Do we have any questions? So for now, doesn't look like. Let's just give the time for people to ask the question. Maybe in the meantime, so yeah, I was particularly interested about that interpretation that you, physical intuition that you give to explain this difference between a bosonic and fermionic system. And I think it's, I mean, from what I understood, it's related also to the steady state. So could you please just come back briefly on that?
Sure. Yeah. So just to reiterate the physical intuition that I have for the emergence of this difference between the bosonic and the fermionic behavior. So if we think back to the expressions for the expectation values, we have this Q star factor that determines how adiabatic the isentropic strokes are. And if we take the limit of that Q star goes to 1, corresponding to perfectly adiabatic strokes, we see the difference between the bosonic and fermionic performance vanish for quasi-static strokes. And so this would correspond to perfectly adiabatic strokes where we have constant occupations of the energy levels. And so the statistics, which play a role in determining, you know, this counting of how many particles can occupy each state, doesn't play a role in that case. But then it starts to play a role once you have non-adiabatic strokes and you have changes in energy level populations, and then these statistics start to matter in the dynamics of the engine. And then in terms of whether or not this is steady state performance, so here we're looking entirely at average behavior for each stroke.
Okay, yes, yeah, no, but when I'm in steady state, I was referring to the steady state of each thermal stroke or
Yes.
Yeah. Okay, I see we have one question. That's a long question. So I'm going to read it. So if we introduce interaction to the bosonic case and take infinitely repulsive interaction to the Tung's limit, where the bosons behave an awful lot like fermions, do you think we will see an identical performance with the standard non-interacting fermions? There's still a difference in the symmetry of the wave function of between infinitely repulsive bosons and non-interacting fermions in this case, of course.
Yeah. I mean, that's exactly what we would expect, right? And the preliminary results we have for the interacting case, we see exactly that that effect. That as we increase the contact, so what we see ultimately for a contact interaction is that it plays no role in the fermionic behavior, which makes sense because fermions will never experience a contact interaction. There's zero probability that we'll ever find them at the same location anyways. And as we increase the strength of the contact interaction for bosons up to a strong repulsive interaction, that the performance converges exactly to the fermionic limits.
Okay, all right. Thank you for this explanation. So I think we can move to the next talk also because we're running a bit late. So thank you again.